All right, gang, STAT1800. I got to tell you, this is the third time I've started this video. I've had a coughing attack in the previous two videos, so I shut it off. I'm not shutting this one off. If I have a coughing attack, you guys will have to just have to suffer through with me. The purpose of this video is to work some of my math lab examples, things that are going to be similar to things you're going to encounter on your assignment. I think the videos so far have been not as structured as I prefer, but I think that approach just worked better with this content. Okay, and this video is really to provide structure and again work examples that you're going to be required to work for your grades. So I had a student in here the other day who, and again I'm putting this video up for fall 2017, and he told me, he said, well, Dr. Darver, we really don't watch those not for credit assignments anyway. So, and you know, I don't know. That's up to you. I would think that they'd be extremely helpful, especially in long term preparing for the final exam. So, guys, let's get out of here and go to Google Chrome, and what you'll see. You'll see a demo, multiple regression, not for credit. Now, this is right after assignment number 15 for this term. But if you're taking this in the summer, there's a chance that multiple regression assignment will be something other than assignment 15. So anyway, whatever the multiple regression assignment is, it's right after that. So I think you guys will actually go through it up here through homework. So I'm going through it through the instructor mode. But anyway, when you open up, you'll see the first assignment. I'm sorry, the first question. You'll see that you have a partial ANOVA table, and again, I've already started this, and I had a coughing attack, so I had to stop. So you see, I've already answered the first question. But guys, to get the mean square for the regression, you just take the sum of squares regression divided by the degrees of freedom for the regression. So 30 divided by 2 is 15 when rounded to 4 places. So to get the mean square error, we're going to take 160 divided by 23, and we will get 6.9565. rounded to 4 places. Now, the next thing it's going to ask is for the F statistic, and remember the F statistic is the mean square for the regression divided by the mean square for the error. So if we take 15 and divide it by the answer, feel another coughing attack coming on, we get 2.16. Well, 2.16. rounded to 2 places. Now, determine the null hypothesis. We have 2 independent variables, so we need 2 betas in the null hypothesis. And when I look through this, A and C can't be true because the null hypothesis assumes that the slopes are equal to 0. So the only 2 that has that condition met, excuse me, guys, is B and D. Now, B is incorrect because B in the alternative says that these slopes aren't necessarily equal to each other. They could be equal to each other. The alternative is supposed to be that just, at least one of those is not equal to 0. So, guys, clearly D is the correct answer. Now, the next thing it wants us to find is the p-value, and that's for the 2.16. So, guys, if we go to StatCrunch and go to F, and we go back and look at our degrees of freedom of 2 and 23. And we want the value to the right of our F statistic, which is 2.16. And we want the area up there. So the area here, and we want that rounded to 3 places. So it's 0.138. Isn't technology wonderful? Well, it is when it works. Now, what conclusion can we draw? Well, we fail to reject the null. And if we go back to the problem above, we're failing to reject that the slopes are equal to 0. So we're looking for the term insufficient evidence. So it's either B or D. So there is insufficient evidence of significant linear relationship with at least one of the independent variables because the p-value is greater than the level of significance. So guys, it turns out it's B. It can't be D because it says that the test statistic is less than the level of significance. Well, guys, the test statistic, easy for you to say, creates the p-value, and that's what we compare to the level of significance. All right, compute the coefficient of multiple determination r squared. Well, guys, what I'm going to do here is I'm just going to calculate r. I'm going to calculate r squared. In one of the videos, I said that we could always find that by taking the sum of squares for the regression divided by the sum of squares for the total. So if I take 30 and divide it by 190, I get 0.15789. So again, r squared is the ratio of the sum of squares for the regression or the model, depending on the way it's provided, divided by the sum of squares total. So 30 divided by 190, and it says round to 4 places. So I'm going to put in 0.1579 there. Now, interpret the meaning of the coefficient of determination. So the coefficient indicates that 15.79% of the variation in the dependent variable can explain by the variation in the independent variables. All right, guys, the next problem, compute the adjusted r squared. If you noticed a little technical glitch, I had an issue with my document camera, so I had to stop that video and I'll just put them together, and not a big deal. All right, compute the adjusted r squared. I didn't really want this problem to be part. I wanted you to be able to get the adjusted r squared using StatCrunch, but it turns out you can't here because you're just given the partial ANOVA table. But you know, I don't think there's any harm in us actually using the formula. So let's take a look at the formula. And so the adjusted, if I can remember it, the adjusted r squared formula is 1 minus a bunch of stuff. So it's 1 minus r squared over n minus 1, I do believe, minus n minus k minus 1. Now, if you look at this part right here, this n minus 1 is really just the degrees of freedom for the total over the degrees of freedom. This n minus k minus 1 is just the degrees of freedom for the error. And since we're given partial ANOVA table, easy for you to say, this is going to be easy stuff to get. So we have 1 minus, we saw that the r squared was 0.1579. And we can go back and get the degrees of freedom for the total and the error. I believe it's 29 and 27. No, it's 25 and 23. Good thing I checked. Now, if we can put this in our calculator without doing something really goofy, life is good. So guys, let's first of all go 1 minus. I'm going to start on the inside here and then work my way out instead of trying to do too much in the calculator at one time. What was it, 7.9 or 9.7? 7.9. So I'm going to take that and get that going in the calculator. And then I'm going to multiply by 25 and divide by 23. And then I need to take 1 and subtract that answer from 1. So that's an easy way to do that in your calculator. So the answer I get is 0.0847 for the adjusted r squared. So 0.0847. Which is not much. You know, to have an adjusted r squared when you control for your sample size and the number of additional variables, to only have about 8% of the variation, you know, that's not much. All right, so the production of wine in a multi-billion-dollar worldwide industry, or the production of wine is, in an attempt to develop a model of wine quality as judged by wine expert. Data was collected on red wine variants. Guys, it's the first time I've read this, so you're reading it along with me, hopefully. So we fit a sample of n equal 45 wines. So guys, I know that n is equal to 45, so I'm going to write that down. The model was used to predict quality. So my y is wine quality. Measured on a scale of 0 to 10 based on alcohol content and the amount of chloride. So guys, we have 2 predictors. Now just to give you an idea of what I'm doing over here, I'm writing down some information that's going to be needed for me probably to work this problem. All right, so I have a sample size of 45. My y is wine quality, which ranges from 0 to 1 or 1 to 10, I forget. Not 0 to 1, 0 or 1 to 10, and we have 2 predictors, so k is equal to 2. All right, so let's see what kind of craziness we can get into. Determine whether there's a significant relationship between wine quality and the 2 independent variables at 0.05. What are the correct hypotheses? Well, the correct hypothesis, since we only have 2 predictors, would be B1 equal B2 equals 0. And then we would have at least one B sub j not equal to 0 for j equal 1 and 2. So guys, this would be the correct null and alternative. Now calculate the F statistic. Well, this is a lot like what we did before, except they only give the sum of squares regression. I'm going to write this down because we want to get out of this. So the sum of squares regression is 25.424, and the sum of squares for the error is 36.929. So we need the F statistic. All right. So guys, let's see what we got here. We got this ANOVA table that keeps rearing its ugly head. So we've got the regression, the error, and we got the total. And we need our sum of squares, we need our degrees of freedom, and we need our mean square to be able to get the F statistic. And it turns out it's not that difficult because we know that our sum of squares for regression is 25.424. We know our sum of squares for error is 36.929. And I'm going to go ahead and create my sum of squares total. So, and you know, that's found easily by just adding the 2. Okay, make sure I didn't do a typo. So it looks like 62.353. I don't know if I'm going to need that, but I'm going to probably suspect they want me somewhere along the line to calculate r squared, which will be that number divided by that number, but don't know yet. All right, so next we've got Two predictors, so the degrees of freedom for the regression are 2. We have a sample size of 45, so I know the total degrees of freedom is 1 minus that. And I know these two things have to add up to 44. This number plus this number has to add up to 44, so that has to be 42. Now, to find the mean square, I take 25.424 divided by 2. Is 12.712. And I take 36.929 and I divide it by 42. So I get 0.8793. Now to get my F statistic, I'm going to divide 12.712 by the answer. And I get 14 point, I don't know how far it's going to want me to go out, but I get 14.45758. So I'm going to write all that down so I have enough information. Now, let's go back to the problem. The F statistic, it says round to 2 places, so I'm going to go with 14.45. And we have an issue. All right, let's. I kind of wish this hadn't happened, but let's check our work. Make sure we didn't do a typo. So 25.424. Sum of squares error was 36.929, and we have 2 predictors, and we have 45 wide. All right, let's see if we can find our mistake. It's probably something goofy that I did. So 45, we have 2 predictors. So 45 minus 2 minus 1 gives us 44. So the degrees of freedom look good. So let's. I have no idea. So let's try 25.424 divided by 2. Divided by 36.929 divided by 42. And actually I get, that way I get a 7 there, so I get 14.46. Surely to goodness, they did not count 14.46. That's absurd. I'm sorry, ladies and gentlemen, that's absolutely absurd. But, well, whatever. Let me show you what the difference I did. Instead of, you can see right here, what I did is I took the answer and divided by 36.929, and then I took 12.712 divided by the answer to get 14.457. Oh, well. Yeah, I don't know. Did I just did I just put that down wrong? Guys, I think I just looked at the calculator incorrectly. All right. Anyway, that was just one of those things. P-value, let's calculate it. So we're 14.46. And we have degrees of freedom 242. And we get 0.000, so 4 zeros and a 2. So if we go to 3 places, so it's just going to be 0.000. I was going to say I'm going to throw my computer through the door if that comes up incorrect. All right, since the p-value is less than the level of significance, we're going to reject the null hypothesis. So there is sufficient evidence to conclude there is a linear relationship. Interpret the meaning of the p-value. Now this is interesting. So the p-value is all about the test statistics. So we know that this or this has to be the correct interpretation. It's not the probability of a linear relationship. It's the probability that the overall test statistic is greater than the sample result, assuming there is less than the sample result, assuming there is no linear relationship. So the p-value is the probability of getting an overall test statistic equal to or greater than the sample result. So guys, since our rejection region is in the tail to the right, which indicates greater than, higher than, we would choose part C. Well, just as I expected, we're going to have to calculate the coefficient of multiple determination r squared. So guys, that's the sum of squares for the regression, which is 25.424, divided by the sum of squares total, which is 62.353. And guys, rounded to 4 places, I get 0.4077. So the meaning of r squared, the coefficient indicates that 40.77% of the variation in our y, which is wine quality, can be explained by the variation in chloride and alcohol content. I figured this was coming. So guys, let's just do it. So we have 1 minus 0.4077 times the degrees of freedom for the total, which is 44, divided by 42. And take 1 minus that answer, and I get 0.3795. All right, question 3 of 5. Are we having fun yet? All right, profitability remains a challenge for banks and thrifts with less than $2 billion in asset. The business problem facing a bank and analyst relates to the factors that affect return. So it looks like they've done on 20 community banks, where Y is the ROA percentage, X1 is the efficiency ratio, and X2 is the total risk-based capital in percent. All right, so this is going to be a fun question, right? So we have our data, so let's put that into StatCrunch. And it looks like to me from the problem we want to predict ROA from the other two. All right, so I don't think I really need this one anymore, so I'm going to get rid of it just to eliminate some of the clutter. So guys, I'm going to go regression, multiple regression, and my Y, I want ROA, and then I want these two variables to be the predictor. Now, I want to save the residuals, and I want to save the predicted values, because it looks like I'm going to create graphs based on those. Now let's check our model with the one they got. So I got negative 5.62, negative 5.62, negative 0.68. So guys, all looks good in the world of matching up our models. Now plot the residuals versus the predicted values. All right, so what I want to do, I want to close this down, and I want to go to scatter plot. And as my X, I want my predicted values, and as my Y, I want my residuals. And I get kind of a straight line there. So the one I'm looking for has these three. I'm going to look at those 3 dots and then something up there. So it looks like to me that this D over here is the one that most closely matches. Okay, plot the residuals versus x1. So it looks like to me x1 is the efficiency ratio. Now, this kind of looks like a vertical line here, and I've got a couple of points up here to the right, so that's the characteristic that I'm looking for. Wow, I don't really see anything that that looks like that. That's no fun. Let's. So it looks like X1. It ranged from 25 to 100. And I'm from, oh shoot, guys, I did that wrong. I chose the wrong one. I need the X to be the efficiency ratio with the residuals. All right, much better. I'm looking kind of at this pattern. So kind of looks like to me that well, that's kind of a hard determination, isn't it? I don't really see anything that's really doing it for me. Well, guys, that's kind of hard, but of the ones that I see, I'm probably going with D. That's a tough question. It takes a little bit of creativity to figure that out. So guys, now we're going to just look at the residuals over the other X value. That's total risk-based capital. And, we've got a couple of points up here. I don't know. Let's see if we can match it up. It's kind of hard, isn't it? Well, guys, this is very interesting. Looks like to me that so we're going from 10 to 30. Oh, guys, it's backwards. We have the residuals. The residuals should be the Y. See, I'll tell you what's getting me messed up is when you do the regression, the Y comes first, and I'm just completely blowing it. So now we've got the X on the X-axis and the residual on the Y's. Guys, I'm usually not this out of it. Okay, so we're trying to find the one that goes, looks like that. Looks like to me it's probably C. All right, well, that was fun. Plot the residuals over time. Guys, there is, doesn't look like this is overtime, so time doesn't apply. Then we'll get into that more. The Durbin-Watson statistic, we'll get into that more in additional videos, but it's not going to be following this one. So in the residual plots created, is there any evidence of violation or regression assumptions? So not really. I don't really like that, but it looks like there's so I would say the appear randomly, so I would probably go with D. A and D. I guess that's subject to interpretation. Actually, there is a U-shaped right there in B, and there is kind of a U-shaped right there. So, so I guess it's looking for this. All right, play the game. I've done a lot of this, and I've seen a whole lot of publications with residual plots that looked worse than the ones that were provided there. Okay, let's go on with the wine stuff. Um, Same thing, alcohol content, amount of chlorides were given, not in the NOVA table here, but a coefficient table. So construct a 95% confidence interval. So we have a sample of 40 wines. Let's see how we do that. Um, All right, guys, remember that to estimate, say, beta 1 in this case, we take our estimate and we add and subtract margin of error. And this beta 1 is plus or minus our T critical times the standard error for beta 1. Now, it turns out from our output, we got two of these, all right? So we're constructing the population between wine quality and percent of alcohol. So guys, we have tunnel vision on this line right here, the second line. So the coefficient is 0.45826. The standard error is given in the output. It is 0.10871. So what we have to do, remember we're doing a 95% confidence interval, is we have to find the T critical. So guys, statistics, calculator, T. We want between. We want 0.95 there. And we have to come up with our degrees of freedom. Now guys, remember our degrees of freedom is N minus K minus 1. So we have 40, so our N is equal to 40. We have two predictors, so subtract 2. Subtract one more, actually for the intercept, so we get a degrees of freedom equal to 37. So the critical value is going to be 2.0262. So guys, back over here, what we need to do, let's forget that. We need to be able to put that in our calculator and get the values, the endpoints. So let's go 0.45826 minus 2.0262 times 0.10871. And then I want to do the same thing. Just change the minus to a plus. Now, if I can put that in there without, let me again show you, so you can pause screen if you need to. So if we can put this in without a typo, so 4 places, so I get 0.2380 up to 0.6785. All right, at the 0.05, determine whether each independent variable makes a significant predictor. Now, the reason I chose this is now we looked at the overall model, the ANOVA table. Now we're focusing in on alcohol and chlorides individually. And you can see that both of these are statistically significant by looking at the p-value. So the first one I want is to test that the first slope is equal to 0 versus not equal to 0, so that's an easy choice. The T statistic is given in the output. It's 4.22, no calculation needed. And the p-value is given in the output. It's 0.0002. Reach a conclusion for X1. Well, we reject H sub O. There is sufficient evidence that X1 makes a significant contribution to the model. All right, now we're going to focus on chloride. So again, B2 not equal to 0, B2 equals 0, B2 not equal to 0, same format. Test statistic is negative 2.54. That's easy, just don't make a typo. And the p-value is 0.0077. Reach a conclusion. Our p-value is less than our alpha, so we reject the null. So there is sufficient evidence to... All right, on the basis of the results, indicate the independent variables to be included. Well, guys, we should include both x1 and x2. All right, gang, this is the question we've been waiting on, the last one. All right, suppose x1 is a numerical value and x2 is a dummy variable. And the regression equation for a sample of 23 is y hat equals 6 plus 3x1 plus 2x2. Interpret the regression coefficient associated with variable 1. So holding constant the effect of x2 with each increase of 1 unit in of x1, y increases, because it's positive, by 3 units. Now, x2 is a dummy variable, so that means that a change in 1 unit actually compares whatever we've coded as 1 to 0. So holding constant the other variable, which is x1, each increase of 1 unit of x2, positive 2, so that's increases by 2 units. Wow, that's it. That's cool. Guys, I hope this helped. Sorry about the sloppiness on the regression plots. I'm a creature of nature, I guess. I was so used to y going first when we run the multiple regression model that I got sloppy. So it happens. I'm blaming it on the allergy medication that I'm taking, and I'm sticking to my story. So guys, I hope this helped, and I hope you guys are having a great semester. And man, I tell you what, final exam is creeping up on us. So probably within the next couple of days, I'm going to post a final exam folder with some information. You'll have a study guide. I intend to probably put up 2 study guides for part 1 and part 2 of the class. And then your final exam will closely resemble the 2 study guides. So guys, take care.